we want to find a potential function f, and you'll remember that that means that del f is then going to be equal to our vector field, it's a fair amount of work. So we want to make sure that before we do this, we check to see whether or not our field is conservative. And I've done that already, and it is. So now we're guaranteed that we can find the gradient of this potential function such that it's equal to our vector field. So let's just remind ourselves how these two things connect. So if I take the gradient of f, it's supposed to be equal to the field, and we do that by taking the partial of f with respect to x, y, and z. And we then see these particular quantities represented in the vector field itself. So the partial of f with respect to x is given as y squared. We also have that the partial of f with respect to y is given as 2xy plus e to the 3z. And finally, the partial of f with respect to z then is equal to 3y e to the 3z. Now we don't immediately need all of these equations. I'm just going to grab the first one here to get us started. And it's somewhat systematic in how we build this out. So we'll find a function f so that the partial of f with respect to x is equal to this y squared. And then we'll use that new function to help us build an equation for the partial of f with respect to y. And once we have that, then we'll build it to make sure that it matches up with the partial with respect to z. So again, I'm going to take this first component here, the partial of f with respect to x, and we're going to anti-differentiate with respect to x because we know when I differentiate I'm supposed to get y squared. So that would imply that our potential function f of x, y, z would have to be equal to x, y squared. Again, anti-differentiating this with respect to x on both sides. But of course we know as we anti-differentiate we end up with a plus c usually. In this case, because it's a partial derivative, we don't just get a plus c, we get a whole function out of it. So we know that function then could potentially be a function of y and z together. Again, if we take the partial derivative here with respect to x, in fact we do still get our y squared back. So we want to make sure that as we're anti-differentiating, we're accounting for the possibility that there's an entire function that might be represented as more than one variable in that anti-differentiation process. So now I think I've got this as my potential function. I just have to figure out what this g of yz is. So let's go ahead and now take the partial of our new version with respect to y. And the partial with respect to y then is 2xy plus the partial of g with respect to y, which is just g sub y. Now according to our field, f of y, or f sub y rather, that partial, is supposed to be xy plus e to the 3z. So let's equate those two. Here is what our potential function says, and this is what our field says. So let's equate those as 2xy plus e to the 3z equals 2xy plus g sub y. And what that would seem to imply then, because 2xy is the same on both sides, that g sub y is equal to e to the 3z. So the partial of g with respect to y is equal to e to the 3z. And much like we did in the first round, we anti-differentiated to figure out what that piece would be. Here we would anti-differentiate both sides, and that would end up with a g of yz being equal to, again, anti-differentiating with respect to y, ye to the 3z. But of course, that's not the entire story either, because we took the partial of this function g with respect to y. There could be an additional component there. Normally it's a plus z, but in this case, it could again be an entire function of z. So we have to count for that. Again, the partial here with respect to y does in fact get us back to that e to the 3z. So making sure that we account for those additional components correctly. So now I think I've got this g of yz correct to this point. So I can take this expression and sub it back into what I thought my potential function was going to be. So it looks like we now have a potential function that looks like f of x, y, z equals xy squared plus y e to the 3z plus h of z. So the only thing left to do now is to run through the partial of f with respect to z and make sure that it's equal to what the field says it's supposed to be. So let's take the partial of our potential function here with respect to z and see what we get. So that's going to look like 0 for the first term, 3y e to the 3z for the second term, and the partial of h with respect to z is just h prime or h sub z. So what does the field say now about what that partial is supposed to be? The field says it's supposed to be equal to 3y e to the 3z. So if I look at the relationship between what I thought my potential function was and what the field says that third component should be, we see that it implies that h prime of z is equal to 0. So it looks like there's no function related to that last piece. Anti-differentiating that, you could argue that there is a function h of z that's equal to some constant, and you could throw that in there as well. So as we look through the final form for our potential function, we end up with something that looks like this. F of x, y, z is equal to x, y squared plus y e to the 3z plus some constant c, potentially. No pun intended. So now we've completed that process. I was plugging in course up to here, bringing that down here with this relationship that we found. Sometimes you're going to get something more substantial out of that last function. In this case, it all matched up, so we ended up with that h prime of z being equal to 0. It's a fairly extensive process, and you need to be somewhat systematic about how we work through that in terms of determining what our potential function is. And I guess the other nice thing that we could do is we could go ahead and verify that we've got our potential function here by taking the gradient of it and making sure one last time that it does in fact verify with what the field says that gradient is supposed to be.